For most practitioners, calculating probabilities means using a published table or computer software to obtain the area under a probability density function. Many of the standard probability distributions have the property that their shape can be completely defined by knowing two measures. The expected value of x, or mu sub x, and the variance of x, or sigma squared sub x. Because the former measures the central tendency of x, it is frequently referred to as the mean of x. The expected value operator E in essence weights the values of any function by the probability density function, that is, the likelihood of encountering those values of the function. The variance is one example where we apply the expected value operator to the function that squares the deviation of the random variable x from its mean. It is important to be clear from the context of the work at hand whether we are talking about the mean, expected value, and variance of a random variable x, or the perhaps sample mean and estimated variance of n realizations of x. The square root of the variance of a random variable yields its standard deviation, sigma sub x. Any function of a random variable is itself a random variable. Suppose a and b are constants and x is a random variable. Some useful properties of the expected value operator are that the expected value of a linear function of x will be a linear function, and the variance of a linear function of a random variable ignores the intercept and squares the slope. Suppose the expected value of x is 1 and the variance is 4 and y is a linear function of x. Here a is 5 and b is 3. So the mean of y is equal to 5 plus 3 times the mean of x, or 8, and the variance of y is equal to 3 squared times the variance of x, or 36.